Welcome to Mathematical Methods lecture on recurrence relations. A recurrence relation, or RR for short, is an equation that relates a number an plus 1 to a combination of some previous numbers an minus 1, an minus 2, and so on and so forth. The nomenclature for recurrence relations closely resembles that for differential equations that we discussed in earlier lectures. A linear recurrence relations can be put in the form shown in equation 5.1, where all of the numbers an plus 1, an minus 1 all appear linearly. All other recurrence relations are said to be nonlinear. If we now look at the recurrence relation of the form 5.1, we define the order of this recurrence relation by the difference between the highest index and the lowest index. In the case at hand, the difference between the highest index and the lowest index is given as capital N, and that defines the order of this recurrence relation. The coefficients C0 of n, C1 of n, and so on and so forth are in principle arbitrary functions of the index n. But if they are in particular independent of n, then we say that the recurrence relation has constant coefficients. The function f of n again can be arbitrary, but if it's vanishing, so fn is equal to 0, then we say that the recurrence relation is homogeneous, and otherwise it's inhomogeneous. Let's first talk about first-order homogeneous recurrence relations with constant coefficients. These are recurrence relations of the form shown in equation 5.2, where we have an plus 1 and a constant coefficient C0 an on the right-hand side. These recurrence relations can easily be solved by iteration. So we start out by writing out a1, so the original equation evaluated for n is 0, a1 is equal to C0 times a0. Then for n is 2, we have a2 is C0 times a1, but we know that a1 is equal to C0 a0, so we get C0 Z0 a0, or C0 squared a0. For a cubed, we have C0 a2, but a2 is C0 squared a0, so this is equal to C0 cubed a0. Proceeding in the same fashion, we can then write down the closed form solution for first order homogeneous recurrence relation with constant coefficients, and it's just given as an is Z0 to the power n times a0. Turns out we can use the same technique to solve recurrence relations that do not have constant coefficients, so those where C0 is a function of n. We proceed along the same lines, so we start writing out the recurrence relation for n is 0, which is a1 is Z0 of 0 times a0. Then for n is 2, we have a2 is Z0 of 1 times a1, but a1 is given in terms of Z0 of 0 times a0. So we get the product, Z0 of 1, Z0 of 0. And then we continue in this fashion, and we deduce that the closed form solution for these types of recurrence relations must be given by the product of the coefficients Z0 of I times a0. It turns out that we can even generalize this to inhomogeneous first-order recurrence relations. So those are recurrence relations of the form given in equation 5.8. And the closed form solution is given in equation 5.9. And I leave the proof of this general solution of this recurrence relation as an exercise. Now that we have talked about the fact that first-order linear recurrence relations have closed form solutions, let us now talk about higher-order recurrence relations. These typically do not have closed form solutions, but the exception to this case is in particular the case of recurrence relations which are homogeneous, linear, and have constant coefficients. So these are the ones that I want to talk about. I will take the specific example of second order linear homogeneous recurrence relations with constant coefficients. So those that are given by the equation 5.10. And we will use a solution method that is very similar to that we employed for ordinary differential equations in lecture 4. So basically, we insert an ansatz. An is lambda, some arbitrary function, or some arbitrary number lambda to the power n times a naught into the equation 5.10. And then we sort of see that we have different powers of lambda on both of these sides. So we can simplify the recurrence relation in such a form that we can write it as a polynomial in lambda equal to 0. And this polynomial in lambda is named characteristic polynomial, again matching the nomenclature that we used for ordinary differential equations. The order of the characteristic polynomial always matches the order of the recurrence relation. So here we have a second order polynomial because our recurrence relation was of second order. And we can do basically the same step also for higher order recurrence relations, even though it's much simpler for me to sort of talk only about second order. So in general, the roots of the characteristic polynomial lambda I from I is 1 to n can be either distinct or non-distinct, but if they are distinct, so if all of them are different, then we can write down the general solution to the recurrence relation. For the second order recurrence relation at hand, we can write down the roots in closed form. They're given by equation 5.12. And we find that the roots are distinct as long as C0 is not equal to, C1 is not equal to C0 squared over 4. So in this case, we can write down the closed form solution to the recurrence relation as given in equation 5.13. So we have that an is given as some constant alpha times the first root to the nth power plus some other constant beta times the second root to the nth power. And this being a second order recurrence relation, there are two constant alpha and beta. If it was an nth order recurrence relation, there would be n constants, and these constants, be 2 or n, always have to be fixed to the initial conditions. In our case, that would be the values of A2 and A1, for instance. An important example of such a second order linear homogeneous recurrence relation with constant coefficient is given by the so-called Fibonacci sequence. This is a sequence of numbers that can be obtained by adding the last two numbers to obtain the next number. The recurrence relation for this Fibonacci sequence is given by the following equation. Fn plus 1 is Fn plus Fn minus 1. It is customary to start with the initial condition F0 is 0 and F1 is 1, so that if we plug this into the recurrence relation, we can generate the sequence of numbers. We find 0, 1, 1, 2, 3, 5, 8, 13, 21, 35, 55, 89, 144, and so on and so forth. A little bit of history about this particular sequence of numbers. Those numbers are associated with the work of Leonardo da Pisa, also known as Fibonacci, the son of Bonacci, who lived from about 1170 to about 1240 or 50 in Pisa, Italy. He is famous in the West for introducing the Indo-Arabic numeral system in his works, in particular his publication Liber Abaci, which was published in 1202. Before Leonardo da Pisa's work, calculations were done using Roman numeral systems, which are, let's say, awkward to use in calculations. And he was the one who really sort of championed the use of the Indo-Arabic system into the West, which he himself had learned from traveling with his father, who was a merchant, to distant countries, in particular Algeria, and learning there about the advantages of the Indo-Arabic numeral system. Also in this same book, Liber-Abaci, he came up with a model for rabbit populations, which loosely are as follows. So he sort of modeled rabbit pairs as pairs that produce one additional pair per year and never die. So if we do this, then we started with one pair of rabbits that produces another pair of rabbits. So we have 1, 1. Then the two of them each produce another pair of rabbits. So we have 2. And we get 3, 5, and so on and so forth, which gives rise to the Fibonacci sequence. The original Liber-Abaci has not been has not survived the centuries, but there's a copy from 1228 which survives, and in particular there's a page from this 1228 book that has these margins here which exhibits the Fibonacci sequence. The writing is slightly different from what we have in our current numeral system, but let me nevertheless point this out. We have 1, 2, this is the 3 here, this is a 5, then we have 8, 13, 21, 34, 55, 89, 144, which you can recognize to be nothing else but the so-called Fibonacci sequence. I also want to point out that the Fibonacci sequence is much older than Fibonacci himself. It appeared in particular in Indian mathematics already in conjunction with the so-called Sanskrit poetic tradition having to do with the sort of long and short syllabus that is used in poetry. There's confirmed knowledge as early as Pingala, who lived somewhere between 450 BC and 200 BC, and there's a clear exposition in the work of Viranhanka at around 700 AD. The Fibonacci numbers have fascinated physicists and mathematicians for centuries. In particular, Johannes Kepler noted that the ratio of two consecutive Fibonacci numbers converges to the golden ratio, which itself has an sort of important meaning already since the ancient Greek mathematicians. So if we take fn plus 1 and fn, and we sort of take n to be very, very large, this ratio converges to the golden ratio, which is denoted as phi here, 1 plus square root of 5 over 2. Also, the Fibonacci numbers have the property that if we sum the squares up to some number n, then the sum of squares of Fibonacci numbers is equal to fn plus 1 times fn. One can also look at so-called Fibonacci primes. So these are prime numbers that are part of the Fibonacci sequence of numbers. For instance, 2, 3, 5, 13, 89, and so on and so forth. And there's a conjecture that there are infinitely many Fibonacci primes, but this conjecture remains unproven. What has been proven is that the only non-trivial square Fibonacci is 144, and the proof dates from 1964. And that 8 and 144 are the only non-trivial perfect powers in the Fibonacci sequence. And the proof for this dates to 2006. From our point of view, the Fibonacci sequence constitutes a second-order linear homogeneous recurrence relation with constant coefficients. And as such, we know how to solve these types of recurrence relations. Namely, we solve it using the characteristic polynomial. So for the Fibonacci sequence, the characteristic polynomial is easily found. It's lambda squared minus lambda minus 1. And we can write down the solution to the Fibonacci sequence as some constant alpha times the first root to the power n plus beta times the second root to the power n, where lambda 1 and lambda 2 are simply the roots of this characteristic polynomial, which can be recognized to be this 1 plus minus square root of 5 over 2. So at this point, using the characteristic polynomial, we can already explain why it is that the golden ratio makes an appearance in the Fibonacci numbers. It's simply because the golden ratio happens to be one of the roots of this characteristic polynomial that we have to use. To fix the constants alpha and beta, we then use the initial conditions, for instance, f0 is 0 and f1 is 1, which gives us two equations for the unknowns alpha and beta that we can solve. We find that beta is equal to minus alpha, and alpha is 1 over square root of 5, so we can write down a closed expression for the Fibonacci sequence given in equation 5.22. This closed form expression is referred to as Binet's formula, but it had already been known earlier, in particular by de Moivre and Daniel Bernoulli. Nevertheless, let's recall that the Fibonacci sequence is a sequence of integer numbers, yet the closed form expression given by 5.22 is definitely not exhibiting the fact that we are expressing solely integers because of the effect of the square root of 5s that float around in this formula. Now that we have talked about linear and first order recurrence relations, let me now point out that nonlinear recurrence relations are also possible to study, but they're typically not solvable in closed form. Even simple nonlinear recurrence relations can give rise to complicated behavior that is easily associated with properties such as chaos. An archetypical example for this is the first order homogeneous nonlinear recurrence relation known as the logistic map. The logistic map can be written in the form given in equation 5.23, where we have xn plus 1 is r, some constant, times xn times 1 minus xn, where this constant r is, or this parameter r, is chosen in the range from 0 to 4, such that the real parameter xn is in the range from 0 to 1. For a small value of xn, we can neglect the quadratic term, and then the logistic map models a population increase with rate r, whereas if xn becomes close to unity, then the map models population decrease, for instance through starvation in a system that's limited by a certain amount of nutrients, such as in bacteria. We can now discuss what happens to the map for large values of n as we change the parameter r. In particular, if r is from 0 to 1, then we can solve the map numerically, and one finds that regardless of the initial condition, the value of xn for n tending to infinity always tends to 0. If we then go on and increase the parameter r above 1, then we find that from 1 to 3, again solving the map, one finds that xn goes to a limiting value that's non-zero. It's given by r minus 1 over r for almost all values of the initial conditions. So we can continue to explore what happens if we increase r further. So if r is in between 3 and 1 plus square root of 6, numerically roughly around 3.44, then one finds that xn oscillates between two values, which are given in equation 5.26. If we increase r even further, somewhere between 3.44 and 3.54, then the limiting values are given as an oscillation between four values for almost x naught. And this behavior continues. So as we increase r, then we get oscillations between 8, 16, 32, and so on and so forth, values for x infinity in what is known as period doubling cascade. I have a plot of this logistic map, so the limiting value x infinity as a function of the parameter r. So for r somewhere between 2 and 3, we get this one limiting value r minus 1 over r, which is shown as this single line over here. But as we hit 3 and then continue further, the limiting value oscillates between two numbers shown in these two lines over here. And as we increase r even further, then we find 4 values, 8 values, 16, and so on and so forth. So it becomes complicated very quickly. Also, it should be pointed out that even though in principle we would expect an almost infinite number of limiting values, for instance, for R around 3.82 or something like this, it turns out that in this case there's only a few limiting values. So you can see this by these wide sort of regions here, which show that for special values or regions of R, there is much less oscillation going on. And these regions, these wide regions in this diagram here, are known as islands of stability, basically. We can also talk about similar sort of properties for recurrence relations that sort of give rise to interesting sort of two-dimensional structures. Such a recurrence relation is, for instance, the quadratic map given in equation 5.87. And this quadratic map is now a quadratic map in the complex numbers. So these z and c's here are taken from the complex numbers, and this recurrence relation then is first order inhomogeneous recurrence relation that's nonlinear. If we start this quadratic map with the initial condition z naught is 0, we can define a so-called set of numbers, the Mandelbrot set, which is the set of complex numbers defined by C, such that for n tending to infinity, the absolute value of Z always has absolute value less or equal to 2. So basically, we start with some initial condition, and then we sort of continue evaluating the quadratic map. If the absolute value of Z that we get after a very large number of iterations is above 2, then this initial condition value was not part of the Mandelbrot set. But if by contrast the absolute value stays below 2 or equal to 2, then we say it's part of the Mandelbrot set. I already said that this is a nonlinear first order inhomogeneous recurrence relation. We can sort of visualize the Mandelbrot set by plotting the numbers that are part of the Mandelbrot set in terms of their real part as an x-axis and imaginary part as the y-axis, such that we have basically a two-dimensional shape of points that are part of the Mandelbrot sets and everything else that's not part of the Mandelbrot set. If we then sort of also use color coding to sort of say how quickly, for instance, a number approaches infinity, then we get nice shapes, in particular fractal shapes, which are shapes that have a detailed structure at arbitrary small scale. So let me show the Mandelbrot set in the two-dimensional projection here with the real part of the number and the imaginary part of the number going up here. The black dots here are all points that are part of the Mandelbrot set, and you can see that sort of this Mandelbrot set sort of has this very filigrane fractal structure that sort of extends basically out here. You can also see that it has the property that this shape, this Mandelbrot set here, is self-similar. For instance, there's this region over here, which clearly resembles in shape the bigger region there, and we can zoom into these numbers and find a self-similarity at even smaller scales. So this is a genuine fractal. It has Hausdorff dimension less than 2, and all of this just generated for a simple first-order recurrence relation. With this, I'm at the end of my lecture today. I discussed recurrence relations, and we learned that the nomenclature of recurrence relations is similar to that of differential equations. We learned that we can solve all linear first-order recurrence relations in closed form. We can solve some higher-order recurrence relations, namely those that are linear and homogeneous and constant coefficients in closed form. We discussed the Fibonacci sequence as an example of second-order linear recurrence relations with constant coefficients. And we discussed that nonlinear recurrence relations give rise to complicated behavior serving as simple examples of chaos. And finally, I talked about nonlinear recurrence relations generating fractal structures such as the Mandelbrot set. Thank you for your attention.